Hello, this is Dr. Kozhanov again, and this is part 2 of the online lecture 1. So this is not lecture 1, but this is a lecture 1 after the break. And in this part, we will cover magnetic anisotropy. So there are different materials, and you already know that, for example, if you will take a material in a round shape, or if you'll take a very thin wire, then these materials will have different magnetic properties. And not only that, they will have different magnetic properties. Let's say they will have different, one might have hysteresis curve that looks like this, and this is H, this is M, and the other one might have, let me choose a different color. The other one will have hysteresis curve that looks like this. So it might be very different, and it might depend on the shape of the material. Moreover, so if you will take the material that is shaped like this, like a thin wire, you'll notice that the magnetic properties along this axis and along that axis are different. And you will see something similar to this. So when materials have different magnetic properties dependent on the direction along which they are measured, then this is called magnetic anisotropy. So anisotropy is basically anisotropy implies that we have properties of something that depends on the direction, and here we in particular talk about magnetic anisotropy. So how that can be measured? Well, if you remember, we discussed magnetic the vibrating sample magnetometry. So part of the magnetometer you have magnet. I schematically designate north and south poles, but these are electromagnets, so they can be switched. So in this case, magnetic field is in this direction. And if you place the sample in this direction or in that direction, our field would be aligned with different or in different axis of the material, and we would be able to measure magnetic properties along the material or perpendicular to the axis of the material. Okay, now if you have something, for example, let's take an iron. So for iron, it has cubic lattice, so cubic crystal lattice. Let me choose and go back to my color. So it has atoms. We'll talk about that. We won't go. It's handy to have this grid here. So we have a crystal lattice that forms a cube. I won't talk about different types of crystal lattice. Actually, that would be. No, we will discuss that a bit later. But you might know from the condensed matter physics that we can designate different directions in this cubic lattice dependent on the orientation. So, for example, if I would take this axis, let me say x, y, z, kind of inverted coordinate system, then for x we would have direction which has 1. Let me make it cleaner. We will have it 1, 0, 0, which means that we have 1 along x-axis, 0 along y, 0 along z. That is 1, 0, 0 direction. Correspondingly, z-axis would be 0, 0, 1 direction, and that would be x0, y0, 1 in z-axis, and y-axis would be 0, 1, 0. Now we can take more exotic direction. So let's say we can take this direction that goes through this atom, kind of a diagonal. That would be 1, 1, 1 direction. Now similarly, we can take direction that goes into the negative, and when we take negative direction, we put a bar above the number. So that's -100. Other thing that I would like to introduce here, basically remind you that this is the direction 0, 0, 1. And this direction is perpendicular to this plane. So we can designate a crystallographic direction to the plane, and we would say that this is 0, 0, 1 plane, and round brackets would indicate that. Okay, so now if you take iron, which has this type of crystal lattice similar to that, we would and measure hysteresis curve of it. So we are measuring hysteresis curve. I will draw only the first quadrant of hysteresis curve. So we apply magnetic field and measure magnetization. It turns out that if we measure it along 1, 0, 0 direction, which means this one. If we measure it along 1, 0, 0 direction, then it magnetizes. Let me increase these. It magnetizes pretty quickly. It goes like this and saturates. Well, saturates. So the value is ms. And this is along 1, 0, 0 direction. As I remember, we discussed that before. So the direction on which the object magnetizes fairly quickly or easily magnetizes is called easy axis. And now, if you'll take this crystal and rotate it so that the applied field would be in the direction of 110, so if you look at 110, it is 110, so this is the direction 110 in plane, in xy plane 110. It goes through these and that parts of the cube. Then the magnetization would be different. The magnetization would look like this. So it would go up. It would go fairly quickly up, but then would go down here and saturate. They all saturate at the same level because this, when you apply fairly sufficient magnetic field, you would align all magnetic moments around that. So this is our 110 direction. And I will use the, I don't know which color to use. Let's use red. And it's red here. So if you'll now use this 111 direction, then you will see that it magnetizes. It goes up to the certain level and then magnetizes like this. So this is 111 direction. And that is a experimental measurements, and they were observed. So basically we can see that different directions in different directions in the crystal can give you completely different magnetic properties. So in this case, this 111 is our hard axis of the material, because you need to apply fairly high magnetic field to get it saturated. Now, what can happen is this phenomenon is called anisotropy. We discussed that already. So what can happen is the following. This is a difference. So if you have magnetic field H and M, and for one axis it magnetizes fairly quickly, but for the other axis you need magnetic field to magnetize. This is called easy axis. And that would be a hard axis. So obviously, in different materials, there might be several easy accesses and several hard access, depends on the material. Now, one of the examples of this is again the wire. If you'll take the wire made of the ferromagnet, and that brings us to the compass. So you know there is this device that was used by from ancient times, which was pointing towards the North Pole. If you take a needle made out of steel, and needle made out of steel somehow magnetizes on its own. So if you take a ferromagnetic wire, let's say out of iron or out of something else, then this would be easy access for it. And that would be, oops, let me do a better job here. That would be a hard access. And what turns out that because of the anisotropy, sometimes we would see a spontaneous magnetization of material in demagnetized state. In demagnetized state implies that you are here. You're here, you are at zero magnetic field and you're completely demagnetized, which means that all your magnetic moments are totally random. But somehow material with totally random magnetization gets aligned as if there is an internal magnetic field applied to this. So there is no magnetic field applied, but it turns out that it can be that material gets magnetized. And you can see here that even a small fluctuation of external magnetic field can be sufficient to get it somewhere here, to get it have non-zero magnetic moment and non-zero magnetization. Okay, so this is what we will study. So we will study different materials and see what is the origin of anisotropy in magnetic properties of materials. So we will start with anisotropy origins. Okay, so imagine that you have a magnetic moment as part of your material, and that magnetic moment is surrounded, it's part of the material, so there is infinite number of magnetic moments all around it, all around here. So what it means is that this magnetic moment interacts with this magnetic moment, and this magnetic moment interacts with that magnetic moment and with all of them around it, which means that it doesn't really matter in which direction I will look. In all directions there will be a magnetic moment. So if I introduce a coordinate system here, let's say that would be X, that would be Y, that would be Z, then the interaction energy, if we look, if at any location X, Y, Z, we will have a magnetic moment that interacts with our magnetic moment at the origin. Then the interaction energy would depend only on the distance between this moment and the other one. So here's R, this is another magnetic moment here. So there are two of them. This is R distance. So what it means is that there is no angular dependence. And since there is no angular dependence in interactions between magnetic moments, there is no anisotropy. At the same time, so if you will take a look on elements like iron, for example, iron has lattice that I'll use this. So it has cubic lattice like this with a one atom in the middle. So you can notice, so if for this is example for iron, if you look at the two-dimensional view of this, we will see atoms here. It's kind of a 2D slice. This would be atoms. They are arranged in a lattice. And you already know that. You might know that from the solid state physics if you take it, or you might not know it, but this is what it is. So if you'll take this atom here, so these atom, let me choose different color. There is a magnetic moment here. There is magnetic moment here, and this distance is A. There is another magnetic moment here, and again, this distance is A. So distance from this magnetic moment to that is the same as this to that. So there will be the same magnetic properties along X direction and along Y direction. However, if you look at this direction, I can choose a different color. If you look at this direction, then the distance from this magnetic moment to that would be how much? That would be a square root of 2. And of course, this would be two magnetic moments separated by a larger distance than these two, which means that the interaction along x-axis would be different from interaction along this axis. And that is one of the origins of the anisotropy. So this is called crystalline anisotropy or magnetocrystalline anisotropy. So the other type of anisotropy is the shape anisotropy. So if you take a material, let's say you take a big chunk of magnetic material, iron for example, and if you look at this magnetic moment in the middle, it has surrounding and somewhere in the middle, it is surrounded with magnetic. It is surrounded with magnetic material all around. But at the same time, if you, for example, take the magnetic moment in this corner, then this magnetic moment has only material inside of that cube. There is no magnetic material outside. And therefore, interaction of this magnetic moment would be, with others, would be different than interaction of the magnetic moment in the middle. And in case of the cube, it's less obvious, but if you go back to our wire, so magnetic moment in the wire here interacts with magnetic moments to the left and to the right. There is interactions there. At the same time, there is no magnetic moment here and no magnetic moment there. Therefore, there is less interaction along this axis, more interaction along that axis. So it is long in this direction and narrow in that direction. That's the wire is. And therefore, if we change the dimensions of the shape, then we will have different interactions between magnetic moments along the wire and perpendicular to that. And again, that forms strong interaction, means that our wire wants to be magnetized along this direction, and that forms our easy axis, and that would be hard axis. So, and what it would mean is that even at zero magnetic field, it might stay magnetized along the easy axis. So that would be easy axis, magnetization versus magnetic field. And at the same time, if you would like to magnetize it perpendicular to the wire, then you would have to apply sufficiently large magnetic field. So that is parallel, that is perpendicular to the wire. So the effect of the difference in magnetic properties induced by the shape is called shape anisotropy. So shape, I'm omitting magnetic. We talk about magnetic anisotropy here. So that is the shape anisotropy. Of course, if you go back to shape is one thing, but if you go to crystalline anisotropy, then if you remember, we would have exchange at atomic level. At atomic level, the exchange interaction is what defines the SI is what defines the interaction, this exchange interaction, and J depends on what type of atoms we have, the atomic radius, but also it depends on how far they're located in the crystal. So if you take different types of crystals, the J would have a different value, and it is a characteristic value for each particular material. So then this J would be different. And if you take this direction along x-axis in the crystal, then R distance between atoms would be equal to A. But if you take the distance diagonal direction, then R would be equal to A square root of 2. It's for this direction. And interaction for atoms placed closer together. Let me go back. Somehow it got moved. Okay, interaction between atoms when they're placed closer together is stronger. So this is stronger. And this is weaker. Stronger interaction implies that we will have a easy access. Magnetic moments would want to interact when they're placed closer together. The interaction would be stronger. And if you go back to this image, you will see that the easy axis is formed by these directions. It's 1, 0, 0, 1, 0, 0. And also, since because of the symmetry, that would be the same for 0, 1, 0 direction, and for this 0, 0, 1 direction. And these two atoms are placed further away from each other. There's actually one in the middle as well. They're furthest from each other, and that would form a hard axis. Okay, so to recap, we talked about two types of anisotropy. One is shape anisotropy. That's induced by the shape of the material, and if you remember, there is a demagnetizing field, which we discussed already, that is proportional to the magnetization. And basically the fact that magnetic moments, even at zero magnetic field, a line along the wire, for example, in this case, can be explained, can be basically not explained, but described as effective internal magnetic field. D is a demagnetizing factor, M is a magnetization. And the second type of anisotropy would be this type of anisotropy. And so this is a crystalline anisotropy. Okay, so two types of anisotropies. One is defined by the shape of magnetic material, and the other one is defined by the crystal structure of the magnetic material. And you would sometimes encounter this might be called crystalline anisotropy, but sometimes we call it crystalline anisotropy. Again, how one would measure these anisotropies? Well, you take a magnet, as we discussed. So you take magnet with big magnet poles, let's say north, and there would be another magnet on the other hand, south or something. North, it's electromagnet, so there should be a coil, and we should be able to control this north or south. You place your material. This is the sample. You place this sample inside of the magnetic field. So magnetic field is always aligned along this axis. And then you can measure hysteresis loop. So you take this axis, you measure hysteresis loop, and you rotate around that axis. You also can rotate about this axis, but it doesn't give us much. This axis doesn't give anything because this axis is aligned along the magnetic field. So there is nothing that we change if you rotate about this axis. But there is also that axis, and you can rotate about that axis. And by rotating it and measuring magnetization along different directions, you can see how different the hysteresis curves are. So this is H, this is M, and for easy axis you would see something like that. It might open or it might not, but it should magnetize at fairly low magnetic fields. For hard axis, you should see something like that. So hard axis implies that, and it saturates. This is saturation plus minus ms. But basically, it requires certain magnetic field to get it saturated. And it implies that we are overcoming it. So if you take the bulk material and you see these different properties, then it might be that you have crystalline anisotropy. Okay. Now, other thing is that we saw that, let me go back to black and let me use bigger this. So let me take a 2D slice of crystal structure. So you have atom here, and let's take cubic lattice. So you might have this crystal. So here's the crystal. And this is zoomed in, and actually have this material. So what you can do with the material is you can apply force and compress it. So basically I would say not force, but apply certain pressure from both sides. And if you apply this pressure, what would happen to the material is that it will get deformed into a smaller shape. And dependent on the material and on the pressure, it might be a lot or it might be a little bit. But what you would see at the crystal, at atomic level, is that atoms, instead of atoms that were here, so if you'll take this as a reference, this atom will move and it will become closer. Let me use bigger. And this atom will become closer, closer, closer. So basically you'll get this crystal that is compressed. And instead of having the crystal A and A, you would have A horizontally. The distance between atoms would be A, but you would have a different smaller distance B vertically, and your B would be smaller than A. So what would happen is that you would move magnetic moments. Notice that these atoms, but they are magnetic moments. You would move magnetic moments closer together, but only along one direction. So what it would mean is that now your atoms are closer in the vertical direction and wider, further apart in the horizontal direction. So what we do, we basically would change their interaction by just inducing pressure. And that would be called a stress anisotropy. So stress anisotropy is, we also can name it stress-induced anisotropy, is the fact that we bring atoms closer together along one dimension. Other thing is that you can compress your material along all directions. That would change the interaction between atoms, but that will not introduce any anisotropy. So stress anisotropy is for uniaxial stress. But now, other thing is that you don't really have to compress material. So imagine that you have one material. Oh, let's take a thin film, or we will call it a substrate. And for example, it can be made of copper. And let's put another material on top. So you put it in the deposition chamber and evaporate, for example, iron on top. So you put, this is very, very artistic. Okay, so you put another material on top. So here's another material, and for example, that can be iron on top of that. So first of all, there are several things happening when you put one material on top of another. One thing is this: for copper, you have a lattice for copper, so-called face-centered cubic lattice. What it means is that you have atom here, atom here. Let me draw it. Here, then let's take here, there, and there, and guidelines. This is cubic. Now what you do, you also place, let me use green. You place atoms in the center of the faces. So for example, this is a top face, and you put atom in the center of each face. So there are atoms on each face. This is on the left face, that would be on the back face, here on the front, and on the bottom face. So face-centered cubic. Now for copper, for face-centered cubic, the lattice spacing A in this case is equal to, I have it written down, 3.597 angstrom. As a note, 1 angstrom is 0.1 nanometers. Or we can write down 1 angstrom is 10 to the negative 10 meters. Okay, so this is copper. Now, if you look at iron, I'll use this. Then for iron, that would be BCC. BCC is body-centered cubic. This is face-centered, this is body-centered cubic. And for body-centered, basically you have these atoms. It's the same. You have atoms. It's also cubic. So you have a cube with atoms in the vertices of the cube, but if you draw the diagonals, let me use now red. If you draw the diagonal here and, for example, there would be one atom right in the middle, and atoms here, there, and there. So these are all iron atoms, but there is it's structured in a way. So for iron, A is equal to 2.856 angstroms. Now what you can see is that if you take copper, and for example we have these atoms which are copper, and put iron on top, blue would be iron. If this atom aligns, then you see the interatomic spacing is smaller than for the copper. So what it means is that this atom would have, it is smaller. But there is interaction between atoms. They form the same crystal lattice when you put one on top of another. So what happens is that iron atoms move slightly out and copper atoms move slightly inward. So copper get compressed and iron basically decompressed, expands. Or no, yes, that's right. So copper tries to move inward, iron moves out. So we are expanding iron. So this is what's happening. Is very similar to this is very similar to compressive strain, and this is similar to strain-induced anisotropy. So I would say that this is strain-induced anisotropy. And the physics of it is, it's very similar to the compression, to the strain anisotropy, but the difference is that we did not compress a crystal. Crystal gets compressed at the interface. Now, of course, and this is the interface here between copper and iron. Of course, that is not happening in the bulk, because the next atom will move less, the next atom will move less, and finally somewhere in the bulk of iron we'll have a relaxed iron structure with a lattice constant equal to this 2.856. But if your films are very thin, then that would be the effect, and therefore in the very thin films you have to take care of that. And about thin films is that whenever your film thickness of the film is in order of less or equal to, let's say, 10 nanometers. But it varies for different material. It depends on the so-called lattice mismatch. So if you take lattice of copper and lattice of iron, they don't have the same value. And this is called lattice mismatch. If you'll take another magnetic material, let's say nickel, for nickel A is equal to 3.499 angstroms. That is pretty close to copper, for example, much closer than for this, for iron. Okay, so now we are talking about anisotropy, and there should be a way how we can describe anisotropy. So we will talk about anisotropy energy. All right, so before we will talk about anisotropy energy, what we can talk about is the following. Imagine that you have a magnetic dipole, M, and that dipole is placed, or let me do this, let me put the magnetic field vertical, B field, and let me put the dipole this way. So if you remember, when we place magnetic dipole in magnetic field, what happens is that we are applying torque. Torque would be M cross B, if you recall that. Now, if we'll talk about the magnetization, then this can be written as magnetization is magnetic moment of unit volume. So we can take this M cross B. V is the volume of material. And so if you have certain material placed in the magnetic field, so of volume V, then that would be the torque. And torque is a vector property as well. Okay, so now if you look at the energy, then energy per unit volume, or this is energy density, energy per unit volume, would be equal to m dot b. So at the same time, the torque applied to that, the value of the torque, can be calculated as d energy, d phi. Let me introduce phi. Phi would be this angle. This is our phi. M b cosine phi. And that would be volume m b sine phi. So you can see the relationship and this, and you can relate it to that, because if you look at the absolute value, that would be a VMB sine phi, angle between the two. So basically, we can judge about the internal magnetic field by measuring the torque. And we can associate certain energy with the torque applied to that. Now, if you look at the anisotropy, let's go back to our example with the wire. Our wire wants to be aligned along the wire, so it wants to be magnetized along the wire. If I apply magnetic field this way, then that would apply torque to this magnetization, and eventually it would align itself, but it starts usually torque, it starts precessing. So now if I take a wire, and somehow place magnetic moment at an angle, phi, what would happen is that there will be certain torque applied, as if there would be a certain effective field inside of that directed along the wire. So basically we can describe our anisotropy by describing how much energy our system would gain, and this energy would be equal to that. How much energy our system would gain if we move the magnetic moment out of the easy axis, for example. So to describe that, let's write it down. So energy, we would say that we will deal with energy density. So we take energy per unit volume, and there would be a constant offset k0 plus k1 alpha square beta square plus square gamma square plus gamma square alpha square. I'll get to what this is a bit in a little bit, plus k2 alpha square beta square gamma square. Okay, so we can express this energy in terms of certain constants, k1, k0, k2, and these alphas. So ki is our anisotropy constants. If you look at the dimensionality, that's energy per unit volume. So this is basically the units of this is joule per, let's say, cubic centimeter or cubic meter, whatever you want to use. Let me use per cubic meter. That would be, this is a convenience of digital whiteboard. Okay, now alpha beta, and gamma are directional cosines. So directional cosines, if you might be familiar with those, but just in case you are not, so if you take x, y, and z Cartesian coordinate axis, and we take a certain point in space, then we will have angle phi here, angle theta there. Then our alpha would be cosine phi sine theta. Beta would be sine phi sine theta. And gamma would be cosine theta. So that is basically, if you take its unit length, this is equal to 1. Then directional cosines are equal to this. So it's basically this component, that component, and vertical component of this particular direction defined by angles phi and theta. So you see, when we and of course there is a normalization. So if you'll take alpha square plus beta square plus gamma square, that should be equal to 1. Now, of course, we will have to choose the direction, because if we have our crystal lattice, so then we'll have to define what are these directional cosines are. And directional cosines in this case, we will take them relative to, that would be the directional cosines of saturation magnetization, MS, relative to crystallographic direction, to the crystal axis. Okay, so now going back to that. So you see energy, this is energy of magnetic moment. And we can think that, well, if you have your material and material is magnetized at H equals 0, we can say that there is certain an effective effective magnetic field that keeps our material magnetized, and that magnetic field certain energy. So, and this is energy density per unit volume, and the value of it is defined by this K, the anisotropy constants, and its dependence on the angle is defined by these directional cosines. Okay, so now what we can do is we can look at different types of anisotropy. And to look at different types of anisotropy, let's take cobalt. Cobalt is an interesting one because cobalt has a hexagonal lattice. So it has hexagonal arrangements of atoms, but it is hexagonal close packed. Let me use thinner wire. So in the middle there is another one, and it's close packed. So if you take round balls and place them, then the closest you can pack those round balls would be the close packed alignment. So basically this will be here, there will be atom there. Hold on a minute. So here in the middle we will have atoms aligned in the middle of these ones. Yeah. Okay, so for hexagonal close packed, what we will have is the following. Let me use thinner one. This direction here, vertical, is 0, 0, 0, 1 direction. Well, there are 4 of them, but you also can use the regular indexes 0, 0, 1. It's a z-axis direction. And the lattice spacing in this direction would be C. Lattice spacing in this direction would be A. And obviously, we can have different materials for which C can be, A can be greater or less than C. So it means that atoms aligned along the z direction have different spacing than atoms aligned in the plane. So what it would mean is that it would have one preferred axis. So any direction in the plane, any direction in 0, 0, 1 plane would be the same, but the direction along 0, 0, 1 axis, this is plane, this is axis, would be different. So we'll have one single axis. So let me choose. Very nice. So there would be this axis, vertical axis in the material along which we'll have different magnetic properties. So this is called uniaxial anisotropy. So for uniaxial anisotropy, energy density can be written as there is always K0 plus K1 sine square theta plus K2 sine 4th theta plus, there can be higher order terms. Now, if you look at this, so what I will do, I will scroll to the left, so you will still see this. So you see this expression for energy. So K1, if we have K1 and K2 greater than 0, and this is the case when A is greater than C, then minimum energy, minimum would be when sine square theta is at minimum. And this is the case when theta is equal to 0. At theta equals 0. So which means that we will have this 0, 0, 1. I will use only 3 indexes, despite that it is hexagonal, because we need only one direction. So that would be an easy axis. This is 1. Second possible case, if K1 and K2 are both less than 0. So if they're both less than 0, then the energy has minimum when sine theta is at maximum. And in this case, that is happening at theta equal to pi over 2 or 90 degrees. And that means that our 0, 0, 1 would be easy plane. So what it means is that and this is the case when A is smaller than C. And you can relate that to the picture here. So if A is greater than C, which means that this hexagon is rather big than tall, it's like this, then atoms interact more along the vertical direction. And this system prefers to be, this would be vertical easy axis. However, if you take material in which it would be rather tall, a big distance between the lattice planes than between atoms, then you would have more interaction in plane. between atoms, and that would mean that our magnetization, this would be preferably magnetized vertically, this would be preferably magnetized in plane somehow, easy plane. Okay, so uniaxial anisotropy is playing a very important role. First of all, there can be more than one axis, but the description is pretty similar. So you know that we already discussed that in material, it is typical that ferromagnetic material can break into various domains with a different magnetization. So magnet domains, they imply that our magnetization is equal to 0 on average, if you have many of those, and they're random, and that is at h equals 0. Now imagine that we have the same material, but with easy axis, with anisotropy, along with easy axis pointing vertical. So what would happen is that despite the fact that we have h equals 0, we would have effective anisotropy field. So effectively, our magnetic moments within domains would prefer to be aligned vertically, and it would break into the domains, but in this case, domains might be all aligned along that easy axis. And so in this case, all domains align along the easy axis. So if you're able to visualize magnetic domains in your magnetic material, then you would see something like that with a striped structure, striped domain structure. Okay, now if you look at the magnetization, if you drop the higher order terms, we can write that energy is equal to volume of the material K1 sine square theta. Now, what theta is, if this is our easy axis, this is the magnetization M, then that would be our theta. Basically, further away we are tilting magnetization from the easy axis, higher is the energy. Our system wants to be in the lowest energy state. Therefore, it wants to get this thing minimized, and if K is greater than 0, then sine theta should be equal 0 and theta equals 0. Now, if we plot this energy as a function of theta, we would have, let's say this is 0, this is pi over 2, this is pi, then there would be minimum here. Minimum would be equal to basically 0. Maximum would be equal when sine theta is equal to 1. That would be, let me move this a little bit. So that would be V times K1, and that is energy. Well, to the best of my abilities, minimum here, minimum there, maximum here. So if you look at the alignment of this magnetic moment, that would mean that here you would have your material with magnetization pointing this way. Actually, no. Let me hold that. Here we'll have it pointing this way along the axis. Here you'll have your magnetization at 90 degrees with respect to the easy axis. And here it's pi, it's pointing in the other direction, to the left. So what it means is that if you have uniaxial anisotropy, then you will have one axis, and it would be energetically favorable for the material to be magnetized either to the right or to the left along this axis. And this is not energy favorable state. Now, if you look at the torque, And if you remember, torque is d e with minus sign d theta. That would be equal to, if you take the derivative, minus v vk1 2 sine theta cosine theta, which is minus, we can get this together, minus vk1 sine 2 theta. So if I plot torque as a function of theta, let me get, oops, kind of goes, yes, 0. So this is 0, pi over 2, pi. Then you will see it goes down, up, down. So if you're here, this is very unstable. The torque is 0 if you're at exactly 90 degrees to these axes, like this case. But if you have any thermal fluctuations, then if you tilt to the right, you'll have positive torque, and it will flip you to your pi state. And if you're here, you'll have negative torque that will flip you away to this state, to theta equal 0. So that is actually widely used. If you know all information in hard disk drives is stored in form of the magnetic domains. So if you have anisotropy, you can get stable state pointing in this direction and stable state pointing in that direction. Then they're equally stable. This would be your logical 0. This would be your logical 1 to store information. Then this is basically the energy diagram for that. That would be your logical 0. That would be your logical 1. And this here is the barrier between these states. So basically you need to supply that much of an energy so that you would switch this state into that state. If this energy barrier is small, and that energy barrier is still defined by this K1 and also the volume of the particle. If energy barrier is small enough, then your thermal K Boltzmann T thermal fluctuations can flip, basically destroy your information. They can flip from this state to that, flip magnetization point to the right into the magnetization point into the left. So, but if you engineer your material so that your anisotropy constant would be high enough, or you would engineer the volume, you see, bigger the volume, bigger the energy barrier. That means that we'll talk about small particles later down the road. But if you take very, very small particles, the volume would be very small and the energy barrier would be very small, and you might be making memory, magnetic memory, that is not stable. Okay, we will get back to this topic once we'll talk about magnetic memory. Now, the other type of anisotropy would be, so we can talk about different materials, but another type of anisotropy I would like to touch on is biaxial anisotropy. Biaxial anisotropy implies that we have two axes, and this is typical for many crystalline materials. So if you'll take energy density for biaxial, we'll have our K0 plus K1 sine square theta cosine square theta. So you can combine these two. That would be K0 plus K1 over 4 sine square 2 theta. Torque by the effective anisotropy field on the magnetization is K1 over 2 sine for theta. And it is more convenient to plot it. So let's say if you'll take, I don't like this. So if you'll take, yes, that's better. X, Y, but again, let's not use X, Y, since we already know this. This would be direction 1, 0, 0. This would be -1, 0, 0. This would be 0, 1, 0, 0, -1, 0. And theta would be in plane angle here. So now we have two dimensions. We have two axes. Then there would be K naught, minimal energy. And let me plot it here like this. And there would be maximum energy. Okay, something like this. Okay. I will also put this axis at 45 degrees, because you see it's 2 theta. It would oscillate faster, and this axis. And I would take a thicker pen and different ink. So we will have minimum here, maximum there, minimum here, maximum there, again minimum, maximum, minimum, maximum. Let me try. And go into minimum, back to maximum, then there, okay. It's not as pretty as I would thought it would be. Now let's, but good enough. So now if we designate this direction is 1, 1, 0, and this direction is -1, 1, 0. This direction is -1, -1, 0. And this one is 1, -1, 0. Okay, if you look at the biaxial anisotropy, and this is kind of a polar plot of this dependence. So we have energy that depends on the angle. You will see that you have minimum of energy at theta equals 0, pi over 2, pi, 3 pi over 2. And you have maximum at pi over 4, 3 pi over 4, etc. So this system has several stable states. So it has stable state for magnetization to point this way, that way, this way, and that way. And in this case, it is equally stable. So we can have magnetization pointing to the left, up, right, up, left, down. And all of those would be stable. So you can think of this so as our theta, this is 1, 0, 0, 0, 1, 0, magnetization, and this is angle. So this shows us the energy of the magnetic moment if it points in a certain direction. So if you have our magnetization pointing at 45 degrees along this direction, it is the highest energy, and it's unstable state. If it points vertically up, it is stable state with the lowest energy, low energy state. Okay, so that is a biaxial anisotropy. Now, how do we measure anisotropy? Well, there are several things how we can measure anisotropy, and I already mentioned one of them. That one would be measuring the hysteresis curve. And if you have hysteresis curve, it can be looking like this, or it can look like that. If you have different properties along different directions, and this is H, this is M, magnetization versus field, so that would be easy axis, that would be hard axis. So immediately we know that we have this anisotropic behavior. The other way to measure it is to remember that we have torque, and torque has it's a derivative. Torque is our dE d theta minus dE d theta. So what it means that if we can measure torque, by measuring torque, we should be able to measure our anisotropy energy as a function of angle. So for that, we can use torque magnetometry. So what happens is, how you do this is you take your sample and you suspend it. Oh no, this is not good. Let me try to use something that would let me to do it straighter. Okay, no, it's not working. Oh, let me do it this way. Okay, imagine this is a straight line. Hard to imagine that though. So you fix strain here and you suspend your sample. This is sample. And you place it in the magnet. So there is a magnetic field that can be not north-south, it can be magnetic field in both directions. What you put weight here. So the strain would be stretched. There is a certain tension in the strain, and when you apply magnetic field, if your easy direction is not aligned along the magnetic field, you would be applying certain torque to that, because if you look at the top view of that, your magnetic moment wants to be this way, but you apply magnetic field that way. So you apply torque to that. So what would happen is that this sample would want to rotate. All you have to do is to measure this rotation. So to measure that, you put a mirror here. You use the laser, you shine the light on the mirror, get it reflected, and detect the deflection of the laser beam. So by measuring the deflection, you should be able to calculate the torque that you apply with a magnetic field to this magnetic moment and to the sample. All right, so we will finish this lecture here, although you can watch it not in one session, but watch it in parts. So end of lecture of online lecture number 1, which was about anisotropy. Okay, so I would encourage you to read textbook by Nicholas Baldwin and look at the anisotropy parts of that lecture. We will continue with talking about anisotropy in the next lecture, and also we'll talk about magnetic domains. All right, goodbye.